Let me introduce Colonel Chappa. We'll get right to it. He's an officer in the U.S. Air Force, holds a doctorate in philosophy from the University of Oxford. His areas of expertise include just war theory, military ethics, and especially the ethics of remote and autonomous weapons. His doctoral research focused on contemporary just war theory. He's a senior pilot with more than 1,400 pilot and instructor pilot hours, many of which were flown in support of major U.S. combat and humanitarian operations. Gattuso joined us here at the U.S. Air Force Academy a couple of months ago, and his presentation was quite fascinating. I'm excited to share it with all of you. So thank you for joining us. And sir, with no further ado, I'll turn it over to you.
All right, thanks very much, Pilgrim. Thanks for having me. Sorry that the tech isn't working out very well. I will just share this brief story. I did a webinar with a bunch of ROTC cadets not too long ago to talk about AI and technology. And through a switchology error, I tried to share my slides and inadvertently shared my Gmail inbox. And I just felt like the old guy who can't be trusted with technology. So it could be worse, could be worse. I'm gonna share my slides and not my Gmail inbox. Would you just let me know when you are visual?
I can see him on my end.
Copy. All right, thanks. I'm going to talk about several things today. I call the talk AI ethics and AI efficacy, but there's kind of a chain of logic that we need to get through to tie those two things together. So the first thing I want to do is try to answer the question, what do we mean when we talk about AI ethics in a military context? And ultimately, what I aim to show is that there's a pretty significant overlap between what we might think of as AI ethics in a military context and what we might call AI efficacy, or getting the answer right, or being operationally successful with AI. So I think there's an overlap between ethics and efficacy, and I want to argue for that over the next several minutes. Whenever we're going to talk about AI and specifically AI ethics, there's a couple of linguistic challenges that are going to arise. So I want to flag those for you so you're aware of them. But I also want to use this time to make it very clear what I mean by the terminology, because you could ask 10 different people who work in the AI space what they mean by AI, and you might get 10 different answers. You might get more than 10 different answers. So the way we talk about it in my office, the Chief Data and AI Office for the Department of the Air Force, is AI is the broad field. AI is a broad field within computer science that aims to use computers to solve problems. If that sounds very broad, that's true. It is very broad. The DoD's definition from the 2018 Defense Department AI strategy says that AI refers to the ability of machines to accomplish tasks that ordinarily require human intelligence. Well, that's almost all tasks that we ask computers to accomplish. So if I go into Microsoft Excel and I've got a bunch of data and I tell Excel to sort my data alphabetically, I'm asking the machine to carry out a task that ordinarily requires human intelligence. So under this broad Defense Department definition, even the sort function in Microsoft Excel counts as AI. That's fine. I don't want to try to debate that. There are people who disagree with that definition, but I want to sidestep that definition to get to the ethics questions. And by that, I mean, I want to focus on machine learning. So machine learning is a family of techniques within the broad field of AI that try to use machines to do predictive analysis on historical data. And so when we talk about AI ethics, we're really focused on machine learning. That's a contentious claim. There are people within the Department of the Air Force who disagree with me about that, but I'm going to try to convince you of that over the next few minutes, that the field of AI ethics is actually focused on machine learning. And machine learning really became of interest in the last 10 or 15 years for reasons that I'll explain in a minute. Within machine learning, there's a smaller subfield called deep learning. This isn't, Rodin's thinking deep thoughts. This is just the depth of the neural network. And so if you have a simple neural network with one layer, it counts as machine learning, but it doesn't count as deep learning. As you start to stack those layers on top of each other, it becomes deep learning that comes with explainability implications and some things we'll talk about here in a little bit. So deep learning is a subset of machine learning. And when I talk about AI ethics, I'm focused on machine learning. Okay, the second linguistic challenge is that we've gotten ourselves into a bit of a bind here in the Defense Department. So in 2020, the Defense Department adopted what they called AI ethical principles. And those principles state that our AI applications in the Defense Department have to be responsible, equitable, traceable, reliable, and governable. And back in 2020, when Secretary Esper adopted these principles, we were perfectly content to call them AI ethical principles. But then the Joint AI Center in 2021 thought, we should be careful about this word ethics, because sometimes people in government hear ethics and what they hear is compliance, right? So with an audience of attorneys, I'm sure I don't have to explain this to you, but think about things like, the Joint Ethics Regulation or the Joint Travel Regulation, where we're given ethical guidelines, which really come down to compliance concerns. And just to indicate for you what a genuine linguistic challenge this is, when I started my first job at the Pentagon, I was in A57 Air Force Futures. They brought me in to be the AI ethics guy on the AI cross-functional team. And I had my first interview with my one-star boss just to welcome me to the team. And we got done with the niceties, and he said, "Do you have any questions for me?" And I said, "Well, I'm just really excited to learn how ethics is going to be relevant to the work that we're doing here." And he said, "Oh, ethics is easy. For instance, I have a friend, he's a retired wing commander. He works at Lockheed now, and he was in town and he invited me to go out to dinner last night, but I bought my own steak. I didn't let the Lockheed guy buy my steak for me. You see, ethics is easy," right? So when I was talking about ethics, what he heard was compliance with norms around what we can accept from contractors, et cetera, right? And so the Joint AI Center said, we don't want people to think that AI ethics is a compliance issue because we don't have the checklist yet that we want to comply with. The work of responsible AI, the work of ethical AI in the DoD is to figure out what checklists do we need, what regulations do we need to produce, what AFIs do we need to write in order to ensure that we're getting these principles right. So the JAIC started using the term responsible AI to capture this broad set of factors that they thought were broader than most people interpret ethical AI to be. However, since then, senior leaders, including Secretary Austin himself, have said that this approach, following these principles, he says, we call this responsible AI, and it's the only AI that we do. Well, if we're not careful, that starts to look like all responsible AI is ethical AI, and all AI that we do is responsible AI. Therefore, all AI is ethical AI. Job done. We've done our work here. Let's move on to the next thing. And I just want to impress upon you that I don't think that's what Secretary Austin has in mind. I think he's instead giving us a target to aim at. He's instructing us, he's ordering us to ensure that when we develop AI, we do it responsibly according to the AI ethical principles. So all that to say, when I say responsible AI, I'm using that synonymously with ethical AI. And there are lots of factors that fall into that, and it's not mere compliance. Okay, so let's set those two linguistic concerns aside for a moment. What I want to do here, I know this is a busy chart, I'm going to walk you through it, but what I'd like to do is try to convince you of my claim that AI ethics, or responsible AI, is really about machine learning. So here it goes. Artificial intelligence sort of becomes a thing in 1955. That's when the term was first coined. There's a famous meeting of the minds that took place at Princeton University, off campus, but organized by Princeton. And that was the first time that computer scientists started to grapple with this question of, can machines end up thinking like humans think? And since then, most commentators say there have been 3 AI springs, and those AI springs are separated by what they call AI winters. So AI spring is characterized by lots of energy, lots of headlines, lots of grants being given to AI research, lots of energy and investment around AI. And the AI winters are the opposite of that. People realized that the hype was a little too much. They didn't get what they wanted out of AI. And so they start to restrict the funding, and things are a lot less exciting. So the first AI spring is in the 1960s. That's really largely theoretical. So you can kind of see the little blip there in the green curve. The green curve is the usage of the term artificial intelligence as a percentage of the total set of terms in Google Books corpus in this data. So I'm pulling this from Google's Ngram tool, which allows you to query all of Google's digitized books from 1800 onward. So in all of the books that Google has digitized, the use of the term artificial intelligence appears in green there. So it's barely a blip, right? There's a little bit of interest there, but not much. And that makes sense because in the 1960s, 50s and 60s, really the AI spring there was largely theoretical. It was largely contained to academia, and it didn't result in big funding dollars or commercial enterprises. The big spike there you see in the middle in the 80s and 90s, that's the second AI spring. And what I love about this chart is that the orange line here depicts the use of the term expert systems. So there is an extremely tight correlation here between an increase in discussing artificial intelligence and an increase in discussing expert systems. So expert systems are what we now refer to as legacy AI. That was the AI of the 80s and 90s. And the idea was that a software developer would sit with an operator expert, let's say a pilot, and try to pull out of that pilot's mind all of the decision criteria that the pilot uses to make decisions. And then the software developer would use if-then logic trees to build out the AI system that could automate some of that pilot's work. So think about something like an autopilot. An autopilot is using the decision trees that are pulled out of the human's brain in order to automate some process. Now, what I really want to show you, this is the second thing I love about this chart. If you look all the way to the right, I don't know if you can see my cursor, but I'll put it on right around 2015. So this is 2015 here. 2015, we see the third AI spring start. We're starting to refer to AI, to artificial intelligence, a whole lot more frequently. We also see a huge spike in references to machine learning. Machine learning is the blue line. So those increase together, which means just as the AI of the 1980s and 90s was expert systems, the AI of our contemporary period is machine learning. And the black line is AI ethics. And what I want to point out to you is there is no discussion of AI ethics. The actual data set here is almost all zeros with a few blips here and there, but almost all zero references to AI ethics until boom, 2015. When the machine learning revolution kicks off, that's when the discussion of AI ethics kicks off. So my view, based on this data and my understanding of the literature, is that AI ethics is as a field of study is a response to machine learning. It's not a response to the previous iterations of AI. Okay, that'll come back to haunt us here in a little bit, so just keep that in the back of your mind. So I want to change gears here. That was a lot of table setting about what we mean by AI. There's a little bit more work we have to do here when we talk about AI and autonomy. And one of the reasons for that is that there's this massive literature on AI ethics in the kind of domestic, non-military civilian context. And then when we start to look for, okay, where's the literature on AI ethics in the military context? That literature is almost entirely dominated by discussion of lethal autonomous weapon systems. And what I would like to submit to you is that those ideas are actually conceptually distinct. We should keep autonomy and AI or machine learning separate in our minds. So on the right-hand side of this chart, think about something like Project Maven. We're going to use computer vision, artificial intelligence, machine learning tools to be able to help the imagery analysts identify objects on a video. That's machine learning, but it's not autonomy. That machine doesn't do anything. It provides information to a human who can then do something, but the system doesn't interact with the world, but for its interaction with this human. Autonomy, on the other hand, does stuff out there in the world. Think about the Navy's Phalanx close-in weapon system. That can be, there is a fully autonomous mode. It's not usually engaged, but it can be a fully autonomous weapon system, and there is no machine learning in there. That is much more like an expert system of the 80s and 90s that uses if-then logic to arrive at its result. Okay, we could have a merger of those two things, and that's something like Tesla when you put it in fully autonomous mode. It's an autonomous system that's interacting with the world, but it's running on probably several dozen different algorithms that are trying to identify stop signs and figure out how quickly to depress the brake pedal and all those things that are contributing to the autonomy. So I'm not saying machine learning and autonomy aren't related. I'm saying we should keep them conceptually distinct because they raise different sets of ethical questions. Okay, so what are the ethical questions raised by autonomy? Really, in my view, the literature on the ethics of autonomous weapon systems is almost entirely dominated by questions about human control. What does it mean for a human to exercise an appropriate level of control, an appropriate level of judgment over an autonomous system? So if you'll kind of follow me around this chart at the top left, this comes from a co-authored paper, co-authored book chapter a couple of years ago. But the idea here is if the goal is to shrink the OODA loop, right? If the goal is to obtain decision advantage over the adversary, I want to prosecute my OODA loop faster than the adversary can prosecute his OODA loop. Well, then one thing I can use artificial intelligence for is to get me between the various steps in the OODA loop. So I can use AI-enabled sensing to get me from observe to orient, for instance, right? So those are discrete places where we inject AI to help us tighten that OODA loop. When we talk about autonomy, we're really talking about taking several steps of that OODA loop, a spectrum across that decision cycle, and asking a machine not to have one discrete input, but instead to manage an entire scope, an entire spectrum of that decision cycle. So that's that red band there that refers to autonomy. So if you follow me down to the bottom left, we can think of examples of rudimentary automation. So I'm thinking 1990s era AMRAAM, advanced medium range air-to-air missile. This is beyond visual range, air-to-air kill chain stuff. So think 1990s Gulf War I, an American F-15 pilot is going to pickle an AMRAAM, and as soon as the pilot pickles that weapon, the rest of the mission, the rest of that missile's life cycle is autonomous. It's going to track the target. It's going to do the geometry to close on the target, and it's going to detonate when it gets within a certain distance or when it strikes the target, depending on how it's programmed. So if we look at the traditional dynamic targeting kill chain, find, fix, track, target, engage, and assess, all we're asking the machine to do there is really the engage step, and the human's doing all the rest. In the literature on killer robots, you can think about the campaign to stop killer robots. The assumption there is that the autonomous system is going to accomplish the entire kill chain without any human involvement. I actually don't think we're going to see that in the near future. I think what we're going to see in the near future is that middle line where we expand what we used to ask the machine to do, and we ask the machine to do more stuff. But that's confusing because we often want to talk in terms of autonomous and non-autonomous systems. And I think that's a little bit of a misnomer. I would prefer to talk about tasks that we ask the machine to perform autonomously, because then we can get into a much more nuanced discussion about how much of the AMRAAM's task is autonomous. It turns out quite a lot, but not target selection. Target selection is still a human function. And if I may summarize a huge body of literature, that's the thing that freaks people out in lethal autonomous weapon system, is the selecting of targets. And so you can imagine a system in which the machine is doing quite a lot, but maybe not selecting targets, right? That's a system that might make the public a little more comfortable, despite the fact that we're increasing the scope of the task that we're asking the machine to perform autonomously. Okay, on the right half of the chart, I just have the language from the campaign to ban killer robots. The language they use is meaningful human control. The DoD rejects that language in part because they didn't want to look like they were aligned with the campaign to ban killer robots. So they adopted in DoD Directive 3000.09, which governs autonomy in weapon systems, they adopt language that says appropriate levels of human judgment. An autonomous weapon system has to have appropriate levels of human judgment. I'm sure you have noticed very quickly here that whichever of these terms one adopts, the next thing one has to do is define what's meaningful and define what's appropriate. And those are hard tasks, right? So there's a whole lot of work on how to do that. There's a third family of terms that I actually don't love, but they've become really common. And that's this discussion of human in the loop, human on the loop, and human out of the loop. So a human in the loop is a traditional airplane like we've had since forever. Human on the loop is one where the process is running at machine speed, but there's a human sort of watching, and the human has the disengage function available. And then human out of the loop says the human is just going to release this thing out into the wild. It's going to do what it's going to do, and then it'll come back and let me know how it went. So that language will come up later, but I just want to flag that that's a thing that lots of people talk about. My problem with the terminology is it's valuable only insofar as you define what loop you're referring to, and I think we often fail to do that. So the AMRAAM is a human out of the loop system post-launch, right? If we only look at the life cycle post-launch, the AMRAAM is a human out of the loop system. I don't think that's the way most people think about an AMRAAM. Most people think of that as a human in the loop system, because the part of the loop that they're referring to, that they care about, is the weapon release function. And that part is governed by a human. My only point here is we have to define what loop we're referring to, or what part of the process we're referring to, in order for these terms to be valuable. Okay, again, I know that's a lot of table setting. I want to distinguish between AI and autonomy. I wanted to prove to you, to show you that AI ethics is about machine learning. And now I want to try to identify what is it about machine learning that raises novel ethical questions. So I'm transitioning here from the table setting to the AI ethics issues. This is a picture of goats. I hope what you're asking yourself is, what on earth does machine learning have to do with goats? I will tell you. I think one way we can think about machine learning is that machine learning provides us with goat path solutions. If you're not familiar, as far as I can tell, the goat path solutions term traces itself back to the Spartans at Thermopylae. As you'll recall, Xerxes and the Persians are attacking the Greek city-states. Sparta's the last holdout. They have their defensive position, but they know they're going to lose at the operational level. So they have the vast majority of their forces retreat with the civilians, and the 300, the famed 300, take up that position to defend the narrow pass at Thermopylae. They have a defensible position because it's such a narrow pass, but there's also a traitor among them. One of the Spartans knows about this goat path to get around the mountain. And if you follow the goat path, you can take up a position both in front of and behind the Spartans and win the battle. So this traitor tells Xerxes and the Persians about this goat path. They do just that, take up their position in front of and behind the Spartans. And the Spartans are ultimately defeated with one person spared to tell the story. So what I think is great about this is that the Persians are only able to win the day here because the goats found something insightful about the battle. No person was able to find the path around the mountain. The goats found the path around the mountain. And that enabled this battle to turn in the way it did. But that doesn't imply that goats are better strategists than the Persians, or that they're better tacticians than the Spartans, right? The necessary condition here is not human level intelligence in the goats. It's just the ability in this very narrow task for the goats to be able to learn something valuable, in fact, to the humans. And that's typically how machine learning is going to function. We're going to employ machine learning on big data sets. We're going to ask machine learning to identify for us insights from that data that's valuable to us, the users. And now what that means is sometimes we're going to get weird results, because sometimes animals think differently from the way that we do, right? I have 2 dogs. They're pretty okay dogs. Normally I can leave my front door open, and 9 times out of 10, my dogs are not going to bolt out of the door. But that 10th time, they're going to do something weird, right? So because animals aren't humans, I can't trust the goats to default to the level of human judgment. In the same way, I cannot trust a machine learning application to default to the level of human judgment. So on the one hand, there's a two-sided coin here. We want the machine learning to deliver to us insights from the data. That's the value of machine learning. On the other hand, because machine learning functions differently from the way that our minds function, it is sometimes going to deliver very strange solutions. And that's what we need to be on our guard against. And that's really where the AI ethics field of study comes from, is how do we defend against not just weird results, but weird results that are either dangerous or unjust. So I want to walk you through some examples and try to show how this works in practice. So this is a pretty well-known case in the AI ethics literature. It was researchers from the University of Virginia and University of Washington, and they took this well-known publicly available training data set called in situ. So this data set has 125,000 images, and they've all been labeled by humans across these 5 axes. So what's happening in the picture? What's the thing doing the thing in the picture? What's the item in the picture, et cetera, et cetera. So this is a bird that's catching a fish using talons over water. So for 125,000 images, humans have gone in and labeled these things. So the researchers wanted to develop a computer vision model that could predict what those human tags would be. So they take their training data, which is a subset of the whole data set, and they train their model to try to predict, to try to learn what are the features that are correlated in the raw data, in the image, with the human label. And what they found was that anytime the computer vision algorithm identified the place as a kitchen, 86% of the time, 84% of the time, it identified the agent as a woman. And the remaining 16% of the time, it identified the agent as a man. And that's not the kind of normal distribution that you would expect. You would probably expect something closer to 50-50. So when the researchers saw that output, they thought, that's weird. The first thing we should do is let's look at the data that we just tested the model on. Maybe that data happened to have 84% women. Maybe it was accurate, in other words. And they quickly found that that's not the case. The data had something closer to a normal distribution, but still not 50-50. So they went back to the original data set, the in situ data set, and found that roughly 70% of the pictures labeled as kitchens have agents labeled as women, and 30% have agents labeled as men. And so there's 2 things we need to note here. The first is it's true that this algorithm learned the bias. There was a bias in the training data, and the algorithm learned to reproduce that bias. The second thing to note, though, is that it didn't just give an equivalent bias in the output. This is not just garbage in, garbage out. It took the 70-30 ratio, that bias, and made it worse. It turned it into an 84-16 ratio in the bias. So it actually took something that was ostensibly bad in the training data and made it worse in the result. And one of the reasons for that, when they went retroactively to kind of do the autopsy and figure out what is this model doing, is rather than doing the hard work, solving the hard problem of predicting whether an agent is a man or a woman, which is a hard problem, it thought, well, I can just cheat a little bit. If I can recognize the features in the image that are associated with kitchen, well, then I can just assume that the agent is a woman, and 70% of the time I'm going to be right. So that's what it did, which is what ended up amplifying the bias. So this is the kind of case that comes up in the AI ethics literature. The end result is an unjust distribution of goods and harms. There's a bias here that's related to gender. That's an unjust bias. That's what has people concerned in the domestic context. Part of my task now is to show you how that maps onto our concerns in the military ethics environment. So I just want to sketch for you how the machine learning process goes. Within the umbrella of machine learning, generally people refer to supervised learning, unsupervised learning, and reinforcement learning. And just for simplicity and time, I'm going to focus on supervised learning. It's supervised learning in the sense that we already have labeled data to start with. So in step one, I'm going to collect all this data and I'm going to get my human labels. So in the case we just saw, humans have gone in and labeled those 5 axes that I talked about. Then I'm going to take some of that data, not all of it, because I have to save some of that original data set for the test and evaluation phase. So I might take 60% of my original data, and this is where I train the model. So I'm going to take a model off the shelf. The data scientists are going to figure out what model architecture is most appropriate for the problem that we're trying to solve. And then they're going to train that model to be able to predict the human labels. This is where the feature extraction phase happens. This is where the model learns what are the features in the data that are tightly correlated with the human labels that I care about. And what's important for us to note here is that at this step in the process, these features are opaque to the developer. The software developer doesn't know what features are being extracted from the data. In other words, it doesn't know how the machine is making the determination that it's making, what it's looking at, what has the machine learned is important in making the determination. So then when I go to test and evaluation, I want to take the data that I didn't already use, right? Because if I use the exact same data on which I trained the model, well, then it's going to be 100% accurate because we've already given it the answers to those questions. So now I need to take that remaining 40%, or let's call it 20%, because I always want to have some in reserve for future testing. So I take 20% of that initial starting data, and now I'm going to test the model. So I'm going to withhold the human labels. I'm going to give it this data, see what the machine spits out, and then compare that with what I know to be ground truth. Did it get the answers right relative to the human labels? And then ultimately, I'm going to release it out into the world, and it's going to give me outputs based on the real world input data. So there's lots of ways to categorize different elements, different categories of AI ethics. I'm using a Georgetown CSET paper because, Center for Security and Emerging Technology, they have a paper on AI safety, and I use it because it's simple. They just bin it according to 3 categories. Failures of robustness, which is focused on whether your data was sufficient to replicate or to reflect the real world. Failures of specification. Did you optimize for the thing you actually wanted to optimize for? Or did you inadvertently, for instance, train your model to identify kitchens and then make assumptions rather than actually training it to distinguish between men and women? And then failures of assurance. Did you adequately train the users on the back end, the users and the end result who are going to operate this thing? Do they know what to look for to identify faults? So those are the 3 kinds of failures I'm going to refer to here as we go forward. Okay, so let's take a quick break from the structure of a supervised learning problem. And let's go back to Plato and Aristotle. This is my second reference to the ancient Greeks. I promise it's the last one. So you're probably familiar with the painting, Raphael's School of Athens. There are lots of thinkers from across the ages depicted, but right at the center, we have one of the most important disagreements in the history of philosophy. Plato is the elderly fellow on your left, Aristotle, the sprightly young gentleman on the right. And they're asking each other, where are the forms? Where do ideas come from? We all agree that we have ideas in our mind of what it is to be a tree or what it is to be a person or what the earth is. And Plato says those ideas come from without, those come from beyond the edge of the world, from the heavens, and they're sort of given to us in our minds. And Aristotle, the empiricist, says, no, they're in the world, they're in the thing. If you want to understand what it means to be a tree, you have to go study lots of trees. It's in the thing. But both of these gentlemen and the vast majority of philosophers and psychologists since then have agreed that we have ideas in our minds for what these things are. You and I right now have an idea in our mind of what a tree is. Mine might be slightly different from yours, but I bet it's not that different. And those are heuristically curated over time. We see thousands, we see millions of trees, and we get these robust ideas. Okay, so this is the audience participation portion. I can see the Q&A chat window. So if someone would type in the Q&A chat, tell me something that you believe is common to insects, right? If I think of the idea of an insect, give me one thing that's common to all insects, to the genus of insect. Antenna, good answer. I don't know if that's going to work for me. Someone else. What do they all have in common? Exoskeleton, nice. Okay, we can use exoskeleton, that's good. Normally people say 3 body parts or 6 legs, but we'll go with exoskeleton, that'll work. How about this little guy? Does this little guy have an exoskeleton? I don't think so. He looks pretty soft. But is it an insect? It's a caterpillar, if you can't tell from the picture. It is an insect, right? We just know that a caterpillar is going to enter the cocoon and then emerge a beautiful butterfly, right? So this caterpillar is just a baby insect. It's the pupal stage of an insect. And you and I are okay with that. We're okay with saying things like all insects have exoskeletons. And at the same time, we know that this is an insect. And yet this does not have an exoskeleton. And why is that? Because we have a pretty robust mental model. We have an idea in our mind of what an insect is that's really pretty well informed, right? We've seen so many instances of insects that we have this robust mental model. So when I say insect, you can picture what I'm picturing, something pretty close anyway, and we have this shared model of the world. There's actually a machine learning app. You can get it on your phone. It's called Seek. I use it with my kids because my kids are all into the animals. So you can run your machine learning computer vision algorithm right there on your iPhone. I did. This is a caterpillar from my neighborhood. So I took a bunch of pictures from a bunch of different angles. I ran it through the computer vision algorithm, and it spit out this result. It could identify for me what kind of caterpillar this is. And notice the picture it gives me is not of the caterpillar pupal stage, it's of the full-grown insect stage, right? So the machine learning algorithm does not have a model of the world in its mind. It doesn't know what an insect is. It only knows how to correlate elements in the data with the human labels. So it can get to a place where it can give you really robust responses, but that's not because it has a model of the world in its mind the same way you do. It's because it's seen enough data that it can correlate lots and lots of important labels with lots and lots of features in the data. This is part of the goat path problem. We anticipate that the machine is going to think the same way we do, and it does not do that. And that's how we get some of the weird answers that we get in the machine learning space. Okay, so that was just a quick sidebar to try to impress upon you the machine learning goat path relationship. Let's start to look at some examples where we get those weird outcomes that might have ethical implications. This is a real world case. Amazon several years ago said, we've got our machine learning algorithm running in your instance of Amazon, whether it's the app or online, right? It has its recommender engine that's saying, hey, if you just bought this book, you might like this other book. And in the beginning, that algorithm was rubbish, right? I bought a garbage disposal for my house, and then Amazon's recommender engine said, you just bought a garbage disposal. You might want to buy another garbage disposal, right? And of course, the time in my life that I'm least likely to want to buy a garbage disposal is right after I have bought a garbage disposal, right? But I didn't click. And by not clicking, I'm informing Amazon of the success of its algorithm. And so as you and I went in there and we clicked on the things that Amazon recommended, or we didn't click on the things, it got better and better and better. And at this point, some of the stuff that Amazon recommends, I think, oh, I didn't know I needed that, but actually that hits the spot. So as they gained success in their customer-facing machine learning, they started to look at the back end of the business and say, what else could we use machine learning to automate? And they said, well, we have 10 years of hiring data. Let's do that. It's structured data, meaning I have not just the resumes, but I also know who was hired for a job. So those become the human labels. I can train an algorithm to say what variables are tightly correlated with the human label, got offered a job. And then I can make predictions about the world. In other words, I can predict who should be hired for a job based on a real world resume. Now realize when it goes through this process, the feature extraction step is opaque. And so there's actually, I'm conflating two different stories here just to give you the highlights. There's an Amazon story, then there's another story about another company that did a similar thing. And I'm going to show you the actual features that resulted in these two different cases. So I want to use women's first because it's similar to what we just talked about with the in situ case. So it's not just the case that there was a bias against women. In fact, when they did testing, the tool recommended 0 women for jobs. So 100% of the recommendations were for men, 0% were for women. But when they went back and tried to figure out what features did the tool extract from the data, one of the features was the possessive noun women's, the word women's. And so if your resume says something like, women's engineering school or women's tennis club or whatever, then it actually docked you points. It associated the word women's with a resume that does not get hired. In the other case, it was not Amazon, but an unnamed company. They found that the highest correlation for getting hired was the word lacrosse and the name Jared. So if you are a lacrosse player named Jared, you had a very high likelihood of being hired under this proposed machine learning tool, which neither of these were ever employed, which is why I grayed out the right-hand side there, right? They scrapped it because it wasn't working. But you can see how we're getting into this unjust distribution of goods and harms based on gender in this case, right? Had they employed this tool as it was before they scrapped it, it would have resulted in an unjust distribution of goods and harms. It would have been unethical. Okay, so what does that have to do with us in the military case? There's a couple things to say about this. So one is, I'd like to show you one more time that AI ethics and autonomy ethics are separate, right? So think about this case. This is another real world case where a company called North Point developed a tool called Compass. and it was intended to predict a convict's recidivism probability, right? So the person has already been convicted of the crime, they haven't been sentenced yet, and this North Point company gave this compass tool to judges so that judges could use it, among many other inputs, to determine what sentencing to give the convicted person. And there was someone who was sentenced using this tool, and they sued the company claiming that the outcome was unjustly biased on the basis of race. And so as they went through, the question was, is it possible for this tool to have been biased based on race? And North Point said, no, that's not possible, because race isn't even one of the variables that we include in the data set. We scrub race from the record. So how could it possibly be biased on the basis of race? But remember the men and women in kitchens, right? What was happening there was that the model was using the features correlated with kitchen as a proxy for the harder problem of men and women. And similarly here, when they went to look at which features were most heavily weighted for the model, they found that it was zip codes. And so even though race wasn't included in the data, because in many places across the country, race and zip code are pretty tightly correlated, by including zip code, they were inadvertently including race, not to 100% overlap, but to a significant overlap between zip code and race. And so the critics of this program say that it's unjust on the basis of race, even though race wasn't included among the data. Now, here's what I want to say about autonomy and AI. There are people who seem to suggest that as long as we have a human in or on the loop, as long as we have appropriate levels of human judgment, as long as we have meaningful human control, then we have sort of dissolved all of the ethics issues. And I want to use this case to say that that's just not accurate, because judges really did use this tool, and it really did influence how they administered sentencing. And judges in sentencing, that is very much a human in the loop process, right? We don't get to a sentencing decision without the judge. The judge is a necessary part of that process. So even though there's a human in the loop, if the judge's judgment is being influenced by this tool that has unjust recommendations, that's bad. That's ethically bad, even though we have appropriate levels of human judgment or meaningful human control. So again, just to flag that there for you, that we should keep AI or ML and autonomy concerns separate. Okay, the last thing we'll do here is I want to give you a plausible Department of the Air Force use case. So I wish I could give you real world AI use cases in the military context, but to be candid, we are not, in the DoD, we are not at the vanguard of developing this AI technology. Industry and academia is. So what I propose is that we take the lessons learned from AI ethics in industry and academia, drive those lessons learned preemptively into the Department of the Air Force and into the DoD so that we can prevent some of those errors. So as a result, I don't have real world AI military weapons cases I can give you, but we can probably think through a plausible one, a plausible near-term use case where we can imagine how the concerns that arise in the domestic AI ethics literature are applicable in the military context. So here's my plausible case. Let's say we're worried about a threat. Let's call it China. One of the things we might want to do is identify Chinese aircraft. So I might develop a machine learning model. Let's say it's in electro-optical imagery, right? Just day TV imagery. I might want to train a model that does computer vision, like the examples we've seen, that can identify or distinguish a Chinese PLA Air Force J-20 from an F-35, right? Distinguish their 5th gen fighter from our 5th gen fighter. Okay, so I'm going to collect all this data. I'm going to train the model against the data. I'm going to do the feature extraction, saying what are the elements in the data? What are the variables that are tightly correlated with the human label that I care about, which in this case is J-20. And then I'm going to test it and release it in the real world. Now think about that proxy problem that we saw in the previous cases, where we thought we were looking for one element in the data, but actually the machine learning algorithm bit off on the wrong thing. Think kitchens again, or think, Jared and lacrosse. The same thing could happen here. I can imagine a plausible case here in which what the machine learning algorithm learns to do is identify sharp angles at the front of the fuselage. Because the J-20 has leading edge canards, the flight control surfaces that are right by the cockpit forward of the wings. And the United States Air Force, the United States Navy, we don't have any airplanes that have canards on the front. And so it's possible that if we look at what the feature extraction is doing, it's actually saying, hey, is there a canard at the front of the airplane? Well, the F-35 doesn't have them, but guess what does? Eurofighter Typhoons have canards at the front. So I can imagine a case, if we're not careful, in which our training data set has only US aircraft, which don't have canards. We train our model, and it learns to focus way too heavily on the presence or absence of canards. Then we go to war alongside the Brits, and the Brits bring Eurofighter Typhoons, and now our algorithm is identifying our allied aircraft as adversary aircraft. That would be a failure of robustness in the sense that our training data set wasn't sufficient to reflect the real world. So the solution there would be, let's make sure that our training data set includes not just US aircraft, but also allied and partner aircraft. It doesn't sound like much. It doesn't sound like it's that difficult. But this is the problem. Because they're goat path solutions, we're trying to anticipate errors that are really hard to anticipate. So the question isn't, how do you avoid the canard problem? It's how do you anticipate all the different things the machine learning algorithm might bite down on to give us an answer, and make sure that we're optimizing it for the variables that we actually care about. So it's a harder problem than it sounds. This plausible use case is just one example of how it could bite us in ways we don't like if we're not careful up front. Okay, so I want to return to the chart that I showed at the beginning and re-emphasize the fact that I think what we should be focused on is machine learning. I say this kind of as a policy matter, that when it comes to writing policy, it's really difficult to get consensus on this, because there's team, machine learning is what matters in our day and age, in this third AI spring. And then there's team, all AI is important. We don't want to forget the expert systems. Those techniques that we used in the 80s and 90s are still valuable for us today. All of that's true. I just want to say that from an ethics perspective, machine learning is the family of techniques that raises novel ethical questions. The expert systems of the 80s and 90s don't, or to the degree that they do, we've already resolved a lot of them. And so I want to focus on machine learning because I think that's where the threat is when it comes to ethical concerns. So at the end of the day, when we produce AI models and we keep one eye on the ethics or one eye on responsible AI, one of the things that we'll do is prevent injustice, right? We'll prevent ethical failures. And by that, I'm including discrimination based on race, gender, et cetera. But I'm also including shooting down allied airplanes in combat, right? That is a military ethics concern if we are inadvertently shooting down our friends. But at the same time, we're going to improve model performance. Right. So oftentimes I get the question, if our adversary doesn't care about AI ethics, why do we need to care about AI ethics? My first answer as an Air Force ethicist is because that's who we are. And I don't want that to change. But my second answer is, by looking at the ethics carefully, we will improve model performance. And when I go to war, I would like for my AI models to be better performing than the adversary's models. And so I actually think the tactician and the ethicist here should be kind of standing shoulder to shoulder addressing some of these challenges, because I think they're mutually reinforcing, rather than have the ethicist saying, oh no, slow down, don't go too fast, we need to be careful. The ethicist there saying, yeah, let's be careful, let's make sure we get the right answer. So the top line takeaway here is, when you think about AI ethics in the military context, don't think only about autonomous weapon systems. There is a place for that. You're not going to get autonomy without AI. I mean, I was just at Eglin and got to see that airplane up close, the XQ-58, and it was fascinating to hear how they're approaching the relationship between testing the hardware and testing the AI. AI is absolutely going to be relevant to autonomous systems, but there's no reason to think it's going to be isolated to those systems. Right? If I have an autonomous system that helps me to do target identification on an XQ-58 or whatever the future operational autonomous aircraft is, why wouldn't I also put that same system on the F-35 to support the F-35 pilot? Right? So wherever these questions arise with respect to AI, we have to ask ourselves, is that equally applicable, not just to autonomy, but also to legacy, traditional warfighting? And then also all of our personnel stuff, right? Anytime we're touching people data, things like finance systems and health systems and personnel systems, right? That has nothing to do with warfighting, but it has everything to do with AI ethics as it pertains in the Department of Defense and Department of the Air Force. So in my view, AI ethics touches all of these things. And again, what we should be focused on is machine learning. I'm going to stop there. I hope I've given us enough time for discussion. I'd love to hear from you. I do have the Q&A box here. Feel free to type in the chat or come up voice. I'm going to stop sharing here just so you don't have to look at my slides anymore.
Sure. For the participants, I don't know how to make it so everyone can speak, but if you do the little raise hand button at the bottom of the screen, I can allow you to speak. So feel free to type in questions or raise your hand and I can let you speak your questions.
Okay, the question in the chat is about success and failure in synthetic data to solve the robustness challenge. So the issue there with synthetic data is often it's the case that we just don't have enough data to train the models. And so one thing we could do is develop an AI tool that ingests the data we do have and then produces similar data on the back end of that. And that way we can increase the data that we have. The challenge there is exactly what it sounds like. If the limitation in the original data set is just going to be reflected in the synthetic data, then it doesn't solve my problem, right? So one example of this is from Uber. Actually, I'm not sure if it's Uber or Tesla, but there's a company called Scale AI, and this is what they do. They serve as a subcontractor for companies that need to solve AI problems, and they don't have enough data, so they hire Scale AI to go find the data to scale their AI application. And so the autonomous vehicle case I'm thinking of was birds, right? And so if you have something fly in front of your autonomous vehicle, it kind of matters what it is, right? Because if it's a kid on a skateboard, you really want to stop the car. If it's a bird, you actually don't want to slam on the brakes, right? Because that bird's going to float over the car most likely, and you could cause an accident by slamming on the brakes. And it's really hard to get bird data because, you know, of all the data they're collecting on video, how many times does a bird fly in front of the car? So they had to hire Scale to go out and collect data on birds, but then also synthetically produce data that looks enough like birds that it's distinguishable from the other elements they're trying to identify. So it's really case dependent. I think there's a place for synthetic data, but I worry that some people go into that thinking that it's a silver bullet. And the challenge is the human reasoning that has to go into what does my synthetic data have to look like so that it actually solves the data limitation problem that I started with. And so I think as long as the professionals who are developing that are asking the right questions, I think it can be really valuable. There's another question in the chat. Are the ML failures I'm referring to really failures of the machine, or is it a programmer error? Would a greater diversity of programmers on an ML project reduce the number of ML failures? For instance, would having programmers from the US and UK reduce the number of wrongly identified aircraft? Yeah, so that's a great question. It's a whole system. So modern software development, they talk a lot about DevSecOps. And the idea there is in the old waterfall system, you'd have your developers produce a piece of software and then deliver it to the operators, right? And there's probably some test involved, but they would test it and then deliver it to the operators. And think about, you know, Microsoft Word, right? In the old days, Microsoft would deliver a new version of Word. We would all get it. Lots of people would complain, I don't really like what you did with this or that. And then Microsoft would take that, and 2 years later, they'd deliver a new version of Word, right? That's the waterfall software development model. The DevSecOps model that's become popular in the last 10 years says, what if I put the developer and the operators in the same room, and I constantly have developers pushing updates to the operators, right? And then Sec is security, right? So then I also have the security folks involved in that conversation so that when the developers are pushing those updates, security is on top of it, making sure that we're not pushing bugs that are exploitable. So all that to say, that is absolutely the way that we need to do AI in the Department of the Air Force, is try to get the operators and the programmers in the same room so that we can avoid some of these issues. I do think having the right people in the room is crucial. So if we're serious about international allied partner engagement, then that DevSecOps model has to include operators not just from our Air Force, but also from our Navy, and also from the Royal Air Force, and also from the Royal Australian Air Force, et cetera, et cetera. So I do think that's an appropriate way to think about that. And I think we're trying to get there, but that's a slow process, as you might imagine, for classification reasons. So the question in the chat there is, what's the objection to my thesis that AI ethics is about ML? I don't think it's about AGI. I think it's about what practitioners are worried about is that people like me will come in and think that machine learning is the answer to everything. And so they're really resistant to equating AI with ML, because ML is really expensive. So a lot of people think we're going to do machine learning and then we can replace all of our expensive people with machines. You're not going to replace your people with machines. You're going to swap out your traditional operators with data scientists and software developers, and they're expensive. And so if you can produce a solution that's not machine learning, that uses legacy AI tools like if-then logic trees and knowledge graphs and all that, well, you might have a much cheaper solution that's equally as effective, right? So this is the AFRL's position, is that we should think about AI really broadly so that we don't constantly go for the most expensive, most exquisite solution to the problem. The problem I have as the ethics guy is that when I walk into that discussion and say, when we're talking about ethics, we need to focus on machine learning, I'm talking to a bunch of people who are not ethicists, And so as technologists, they have a different perspective and they really want AI to stay broad. So really it's a matter of just getting everyone to acknowledge that we can refer to AI broadly in general. And then when we talk about ethics, we should focus on machine learning. And that's been an uphill battle for me for whatever reason. Are there areas of AI being developed that you think shouldn't be used? I don't think I can say no in any kind of blanket sense, but I want to be really clear about the relationship between operational risk and what you might think of as technological risk. So, there are, if you use deep learning, deep neural nets, they quickly become unexplainable, where every case I gave you, the developers were able to go back and look at what is the feature that was extracted. When the model gets sufficiently complex, you can't do that anymore. You can't go back and figure out what is it that it was looking at. And that's a real challenge, especially in high risk cases. So I've had some people suggest that, oh, well, we just need a policy that says the Department of the Air Force will not accept unexplainable AI. Or in other words, all of our algorithms have to be explainable. But I don't want to do that, because I could have an AI tool that helps me pick out my socks in the morning. And I'm willing to accept something that's not explainable because the cost of failure is extremely low, right? So what I want to do is match the concerns about the kind of architecture, the explainability, the robustness issues, all that stuff we were talking about. I just want to make sure that's matched to the risk in the use case. So to give you a very real, I think very good example, Air Force Weather, A3W, has a tool that's initially operationally capable. It's IOC, it's not fully operationally capable yet, called Global Synthetic Weather Radar. And for the sake of time, I'll spare the details, but essentially they used a known data set to be able to predict what the weather radar should look like based on what the clouds look like. And that's a really valuable tool if you live on a planet that's covered 70% by water and you have satellites constantly overhead that can see the clouds, right? That means I have a really good picture of clouds on the surface of the ocean, and I have almost no radars on the surface of the ocean. So what if I could predict what the radar looks like, and that could help me find thunderstorms and things like that? Well, that matters if you're flying airplanes over the ocean, which we do on a regular basis. That tool that they have is not explainable in the traditional sense. It's trained on a deep neural net, and there are opaque issues about whether the developers could go back and look and see, but why did it come up with the answer it came up with? And my view on that system is, as long as the operators, I'm thinking more on the aircraft side than the weather side, right? As long as the commanders who are deciding to trust that system understand that limitation, then I still want commanders to be able to have the authority to say go or no go, right? Now, what I don't want to do is get us in a situation where the commander who has the authority to say go or no go doesn't understand the limitation of that system. And that's a workforce development challenge for all of us, is how do we get decision makers to understand this technology well enough that they can make those risk mitigation decisions. So that's an example where I'm willing to take a hit on technological risk, right? Let's go ahead and employ the non-explainable system, because the consequence for failure is non-zero, right? Flying airplanes into a thunderstorm is bad, actually. But if we're talking about kicking off a war, I'd rather have that radar picture than no radar picture at all, right? And so maybe that's a tool that we'd be willing to use despite the limitations. So I want commanders to be well equipped to make those decisions. What books do I recommend? If you're interested, the best book I have read on AI/ML is Janelle Shane's book. It's called You Look Like a Thing and I Love You. She has trained ML to do lots of things. One of the things she trained it to do was to come up with new pickup lines, and that was one of them. You look like a thing and I love you. So that became the title of the book. But it's very approachable. She's a technical professional, so she is doing coding, on ML. But it's really approachable. And one of the things I like, although I'm embarrassed by it, is her chapter 7 of that book is just a hit parade of all the relevant AI ethics cases. And I have spent a ton of time collecting those, like reading the papers and collecting all those so I can give briefings like this. And then I read her chapter. I was like, man, she's already done all this work that I spent all these hours trying to do. But it's a great book, and that's where I would start if I were you.
Okay, we're right about at the top of the hour. So I guess we may have time for one more if there are any more. Otherwise, thank you so much for joining us. This has been enlightening and, quite frankly, fun. This recording will be posted on the LitWork YouTube channel, Law, Technology, and Warfare Research Cell. And I can't thank you enough. If you have any final closing comments, we'll take them now and then say goodbye. And thanks for joining us, everyone. And thank you, Colonel Chappa. Thanks, Katuza, for this insightful event.
Thanks for having me, Pilgrim, and thanks everybody for coming.